All right, thanks. So this talk is not about offloads to smart NICs. It's also not about AI. I'm going to open with that. It's about all the parts of the network card that we hopefully agree on how they should operate. So it's the opposite of all the sort of super cool innovation that we're trying to do. I'm going to introduce the Open Compute project core feature spec that we wrote over the last year and became a spec this summer. And the reason is that I'm here is not so much to tell you that this is the greatest spec in the world, but that it's a starting point. And I want to invite everybody who has an interest in NIC features to contribute, to join, so that we can make it even better. So why are we doing this? There are two parts here, sort of the users of the network cards and the builders of the network cards. And I'm going to start with the users, the operating side. I work at Google. We have quite a few network cards. I've been part of like the introduction of multiple generations of network cards in our fleet, and it's a long process. It's a surprisingly painful process, and for reasons that are not necessary. Like if new features don't work as expected, that's understandable. But if old features don't work as expected, that shouldn't exist, right? So very low-hanging fruit is I've seen recurring the same hardware bugs in multiple pieces of hardware. When we write software comes with tests. When you write hardware, it probably comes with tests, but it's kind of surprising that we don't have a shared test suite for hardware. So whatever a vendor might implement, as a user, I don't see that. I might write a test and it turns out that it doesn't work. There's a disconnect there. A bigger disconnect is in terms of what is delivered and versus what we need. And I think some of these points we've made before, but we need to continue to make them, which is one of the reasons we write a spec. I hope we don't have to talk about this anymore. A lot of network cards support, public protocols, things like Geneve, VXLAN, GRE. A lot of these hyperscale deployments, and I didn't mention that part. Like I work at Google, it's like a big hyperscale deployment. A lot of the hyperscale workloads, we operate in a closed world. So we might start with GRE tunneling or some other common protocol, but inevitably one user wants to add just one field to this protocol header. And now it's no longer a public protocol, right? And a device that only supports specific protocols will break on our custom protocol. So what we want are devices that work protocol independent. And second, I think the scale of operations are sometimes a bit underestimated. Network cards need to scale to millions of active connections, hundreds of thousands of connections coming and going at the same time. So any kind of implementation that says like, well, we need high packet rate, connection rate's not a big deal, that's wrong, right? That is a reason for us to not be able to deploy a card. And we might only find this out as we scale up across our fleet to get to these machines that are at the tail end of the distribution that have the most connections. And then third, inconsistency between cards for no good reason. And the poster child of this is telemetry, right? So in Linux, we have the standard network device stats, and then we have etool-s, where everyone just throws in whatever they think is interesting, and they give it the same name, their own name. So different cards may have the same feature under a different name. Or worse, they might actually have a standard name, but don't agree on the behavior of this is. Like what is a byte counter in the context of segmentation offload, in the counter of various optional headers? It's actually not that straightforward. So we should just once and for all, I guess, agree on how this works and we can move on. And it is important to us because when you deploy a large fleet, we're very reliant on automated monitoring, so ingesting of these counters. And it's not just a session for me to rant over, what's hard. I think writing this down and agreeing what's feasible from a vendor point of view and what's useful from a hyperscaler point of view and really any large operator point of view is good for both sides because I think what usually happens is that an operator will request a NIC with some features, and this request for proposals is kind of written from scratch. It's a rush job. It's incomplete. Like it might have a list of these features need to be supported, but it might overlook the interplay between features, like what needs to do TSO and needs to do tunneling. Like, did we mention tunneling TSO here? Performance aspects, like there's a number on the box that says 800 gig with how many queues? Is this a stable number? If you increase the number of queues, Does this imply that you have some offloads enabled? Then even if it's a complete RFP, it might be an imprecise one, because some of these features that we all agree on, like RSS, are actually not fully specified anywhere, right? There's no read this implementation or this documentation on how these features work. Some of them are, some of them aren't. And the last part is we don't share our tests. We don't share our workloads, right? The example I just gave over that we use custom protocols. So any card that assumes that we use only whatever is an IETF RFC is inapplicable for us. We should be better at sharing how we operate and give representative workloads. So that's essentially what I aim to do, or what we aim to do. Get consistent behavior, get the kind of correct behavior, like bug-free behavior, and get behavior that's fit to purpose. And we want to do this in the open. I think that's a more interesting part, because I think to get a good, comprehensive, correct spec needs the expertise from everybody. Like we all have these little, we've all encountered bugs, but we haven't all encountered the same bugs. We all have some insights, but if we have one-on-one conversations between an operator and a vendor, this gets lost all the time. So there's no competitive advantage here. Let's write this down. Let's share this together in a public format, which also means that anything that's in that spec is you don't need an NDA to read it, and it also has some legal implications in terms of intellectual property and so an open spec has a really big benefits to the ecosystem. And the goal of this is that we basically build a broad market of devices that everyone wants to innovate and specialize in the new features, whether that is virtualization, DPU, IPUs, but at least the core stuff that we all agree on, we can move on. We don't have to, with every new NIC, wonder whether this is working well or not. So with that, we came up with a spec, which is a long document that's fantastic for reading before bedtime. But with it also a test suite, which hopefully allows you to, basically assure correctness and conformance to the spec without having to read the spec, and a short checklist that summarizes all the items in the text, so that ideally the outcome of this is that vendors can essentially self-certify and say, okay, our device implements these features, and it is within one of these basic or optional or advanced modes of the spec. Okay. So again, I mentioned we target hyperscale. It's a bit of a fancy name, but essentially it means large deployments, large fleets, high-end machines. Mostly because it's a large fleet, it means that the machines communicate with lots of other machines. So you have particular problems such as incast to worry about. They are heterogeneous. These machines are not all changed overnight. So you have to work well with other NICs. This is where that inconsistent interfaces comes from. It's a closed world, and we need a continuous monitoring. I already mentioned this. So I think in some ways these hyperscalers are some of the hardest environments to satisfy, and I hope that what we describe here actually applies much more broadly also to other large operators and also to medium-scale operators. The goal here is to only describe what we all agree on. So its core features, or otherwise the controversial table stakes, explicitly no virtualization, no smart NICs, right? That's why I opened with that. Anything that we can't agree on how it should work should probably not be in a shared industry-wide spec. And then the interface, we don't mean to tell vendors how to implement their hardware. Not even the device interface, so no memory layout, registers, no PCI bars or anything like that. It's really, we want to be able to use your network card, and the way that interacts with the operating system is at the device driver level, NDO, net device ops for Linux. It's not OS specific necessarily, because if you look at Microsoft wants essentially the same features, and it's to us to also make sure that between Windows and Linux and other OSs, we request the same features. I think this is one of the pain points currently, and Verdio really shows that Windows requires some individual feature flags that Linux doesn't offer, and it's kind of hard to run a Windows guest on a Linux host, and I think it's for no good reason. It just happened to be this way. So with that, with a group of 4 companies, so this is Meta, Google, Intel, and NVIDIA, we sat down together to write an open spec with features that essentially, Meta and Google are interested in, and I think are representative of what a lot of companies are interested in. And it's really great to work with vendors so that we also get to hear, like, no, what you're asking for doesn't work. We're never going to do this. It helps keep us honest and ask for reasonable features. And of course, make sure that what we ask for is also actually implemented in current generation and upcoming generation network cards. A very important point, what we describe is a blueprint. We have to be realistic. Not every card is going to implement all of this, but also the point is it's a blueprint that's a starting point for companies to have conversations with each other. So if as a company, as an operator, you don't care about a certain feature, just say, like, this part of the spec doesn't apply. And as a vendor, you say, well, we implement it slightly differently. That's fine. The goal is to have a very concise checklist and a little, sort of diff from the spec, like, this is how we differ from the spec, rather than a 10,000 or so page PDF that just argues from scratch as if we don't know what a network card is. So this is the layout of the spec today. We'll go over it briefly. I'm not going to bore you with trying to get through all of it. I'm just going to point out a few small points that are hopefully interesting and that explain why things we all agree on. It turns out if you look closely enough, we don't really agree on them. So that's why it's worthwhile to at least once write them down and to have a common resource to go to. The introduction section is exactly what I just talked about. Like, why are we doing it? What are we doing? What's the goal? What's the outcome? So I'm going to skip that. Then we get to the data path or the I/O API. Modern NICs use asynchronous queues for communication. They are multi-queue devices, and they can run in interrupt or polling mode. All of this is pretty standard. Then you get to the details. Do we want a single queue or post-completion queue model? Probably the latter. I think this week we've already seen multiple use cases of header split. We rely on this at Google for our TCP zero copy receive. So if we don't have header split on a card, it will be an immediate performance regression, a cycle efficiency regression versus our current hardware. So for us, this is a hard requirement. Right? And we give some details on if you implement header split, there are some gotchas on how to implement this efficiently across the PCI bus. So those are the kind of, like, technical details to make sure that no one implements a feature and then finds out that it's not competitive. Increased MTU, also something that's relevant. And then you get to the point of, well, if we have a multi-queue device with large buffers, we're posting a lot of RAM to this NIC that's expensive. There are various ways of condensing the amount of data that's being posted to the NIC, such as having multiple completion queues share a single post queue. There are more of these kind of details on the data path that I will not go into just because we don't have time and I want to focus on other parts. So the design principles, when we get to the offloads, before we go into checksum offload and segmentation, there are some principles which go directly back to that first slide on, like, the problems we've encountered. Ideally, offloads are stateless, right? If you get to choose between an offload that is O1 or an offload that is ON, it should be O1. And this is not just because it's nicer, it's because of the scale that I pointed out that fleets today operate on and the size that machines are, and this keeps going up. And then secondly, it should be protocol independent because of these custom protocols. And it's not just custom protocols. Even if we only would be using, proper IETF protocols, that the open world also changes, and a network card is immediately obsolete the moment it ships, right? A small side point here is that protocol independent is not the same as a programmable pipeline. So a fixed pipeline that supports a list of protocols is the worst option. A programmable one that you can teach new protocols is better, but it's not as useful as a protocol independent one for features that can be implemented in a protocol independent way. And the reason for this is we have to push a new firmware update to the NIC. Now we have a correlated rollout between the software that's trying to use a new field and the firmware, the NIC that has to support it, and correlated rollouts means preparing for correlated rollbacks. And in a large fleet, this is risk and unnecessary risk. So that gets to the oldest offload in the book, checksum offload. One of those things that you would think we wouldn't have to talk about anymore. We know how this works. We all agree how this works. So David Miller gave, in his keynote in 2016 to Netdev, he mentioned that what we want is very straightforward, right? A single linear sum over the whole packet on receive, and on transmit, it's a single linear sum from some offset to the end of the packet, and then written at an offset. Very straightforward. With this, the host can do anything. You have multiple layers of tunneling. Adding checksums for tunnel headers is very cheap because by definition, the inner checksum plus the packet sums up to 0. All of this has been talked about before, so apparently that wasn't effective enough, so that's why we wrote it down this time, the reason why we care about this, so hopefully 2023 is the last time we have to talk about this. Segmentation offload. Most cards today support TCP segmentation offload. TSO is table stakes. I would say that USO or UDP segmentation offload is as well. With HTTP3 and QUIC streaming media protocols, UDP for bulk traffic is big. UDP is simpler than TCP to implement, right? If the payload is a perfect multiple of the segment size, then the UDP header is essentially the same for every segment. So what UDP segmentation offload is just a matter of you take a packet, you split the payload, and you copy the header to every segment. Very straightforward and protocol independent. So we generalized USO to something we call protocol independent segmentation offload, or PISO. With PISO, we can support essentially any tunneling protocol that doesn't encode any kind of fields that differ between the segments. The biggest field that differs between segments is the length field. UDP does have a length field. So if the packet isn't a perfect multiple, UDP needs special support for changing the length field in the last segment. But the host can quite simply just not pass those packets to the device. It's not strictly necessary. Another obvious thing these days, I think, is big TCP support. We want to have TSO and then generally, PISO for packets that extend beyond 64 kilobytes. And then there are a lot of details on how to do TSO well, and these we summarize here, but I also really point to the Linux kernel GSO stack as the source of truth. So the text just summarized what's in the kernel source, but maybe it's a little bit more concise here. For instance, if you have a TSO packet with a fin bit, obviously only the last segment is going to get the fin bit, not every segment. That makes no sense. Push bit is a little bit more less obvious, but the push bit is a really good signal that we reach the end of a TSO train. So on receive, the receive side coalescing, the context can be closed when a push bit is observed, or low latency traffic will have the push bit set. There are more of these details for RSC. Similarly, that essentially mostly comes from the Linux kernel GRO stack. Microsoft has an RSC and this spec, but it's limited to IPv4 TCP, IPv6 TCP. It's quite restrictive in terms of TCP options. So what we describe here and what should be implemented is more generic, supports more protocols, and supports real-life variants of protocols that hardware currently might not apply RSC for. And RSC is a really big cycle efficiency saver in the fleet. Just two more. So timestamping. We've talked about this week. We want timestamping at line rate, not just for P2P, so not just every millisecond in one packet or so. Congestion control, delay-based congestion control, fleet-wide monitoring is my talk yesterday. That's why we're advocating for doing this feature at line rate. There are a lot of standards on how to do timestamping, like IEEE 1588 v2, standards about clock stability. We refer to those standards. We're obviously not re-implementing the wheel here. And then traffic shaping. Traffic shaping is an example that I mentioned here because it's an example of doing an offload in O1 rather than ON. Hardware rate limiters are very useful, but hardware rate limiters is a limit per flow or flow group. So inevitably you get like an N there. And a couple of years ago here, there was a talk about earliest departure time, which is this idea that you can have a single queue basically, but a single structure, and all packets, the host passes the packets to the device with the timestamp associated. And the only thing the device has to do is not send out the packet before that timestamp. And it's the host that has the smarts in logic on computing a timestamp in the future. If there are two flows, one is high priority, low latency, and the other is bulk, the host will know its bandwidth and will add timestamps on those low rate traffic sufficiently spaced so that the low latency traffic is not blocked. There's a lot of complex logic there, but the NIC doesn't need that logic, and it also doesn't need a fixed number of rate limits, because if we have a fixed number of rate limits, inevitably in software we need to have a backup solution, and we need a hybrid with some things go in hardware and some things don't, and it becomes very complicated very quickly. There are a lot of details about protocols. The only one I'm going to mention is anything that's only IPv4 in 2023 is totally unacceptable. So IPv6 first, IPv6 only, one of the two, essentially. And I think I already went into telemetry. Then we get into, we pass the functionality, performance, right? Network cards come with a big number, 200, 400, 800 gig. What does that mean? At how many flows or how many cores do you reach this number? Do you require offloads to reach this number? With certain offloads, do you no longer reach this number? Is this a stable result over time, or perfect conditions only? Like real world conditions that we have other applications running. The memory bus is stressed, the PCI bus is stressed. If you only reach the big line number in an otherwise idle system, that's not very useful. So we suggest also antagonist workloads to test against. We already looked at the checklist. So then we get to the last appendix, which is how to test. This is not normative. This is a suggestion on how to potentially test these features. Configuration is just basically, the util commands on Linux. Functional part is RSS, RSC, like the receive side coalescing. Is it when should you combine two packets, or when is it not allowed to combine two packets? Quite subtle, but quite important for correctness. So what we did, as for starters, is whatever test we wrote at Google to validate hardware and to validate software implementations as well, we sent upstream. So these are in upstream Linux under tools testing self-testnet, test for checksum offload, receive side coalescing or hardware GRO, pacing offload, delivery time, toplets, which means RSS, etc. I have no illusions that this is a perfect coverage, or even that these are perfect tests for the features that they cover. It's a starting point, and I think pretty much every organization that either uses cards or builds them has tests like these. So let's share those tests. If suitable, put them in the kernel. If not, we'll create a shared GitHub project. You can reach out to me if you have tests that you think are useful to add, and can open up and share with the rest of the industry. And for performance, we do something similar. We use Google's Nepper, which is like iPerf or NetPerf. Nepper internally supports having multiple flows, multiple streams, multiple threads, multiple flows and threads, and aggregating the information across them. Built in, supports things like ePOL, so it really maps very well to some of our workloads. And it can do request response, latency type tests, streaming tests. So we essentially have a matrix of tests with multiple cores and flows. You sweep this. We can run it with antagonists. It's a pretty good starting point to have an estimate on what the performance of a net card is going to be in the real world. All right, so that's what in the spec. And then the reason I'm here again is to sort of invite you to join us to make it a better spec, to make it a more broadly carried spec. The first step for vendors is consider certifying your spec. So we'll start with that, which is look at the test suite, run it, validate it, look at the checklist. Like some of it is covered by the test suite, some is just a matter of like how many queues the device can support, can fill it in, and publish a specification. For OCP members, we can basically add a OCP-inspired stamp of approval on a card that meets the spec. And remember, 100% compliance is not the goal. The goal is to see a checklist with a small diff of where the card differs from what's in the spec. And the OCP-inspired cards can be put on the OCP marketplace. So it's also a way to get visibility. So that's certifying devices. We want to improve the spec. I've already asked to contribute your tests. With the tests comes a harder problem, which is how do we test continuously? The sort of the gold standard, the ideal version here would be where we have common CI infrastructure. We have a sort of a Linux image with these tests. You boot the Linux image, the tests get run. It reports with the standard tab format to some centralized system. We're not there, but if contribute tests, but also the CI infrastructure, could we test every upstream Linux kernel or every next kernel? Could we run hardware tests alongside the software tests that we currently have in things like self-tests? And help with the text, right? We review the text that is there, and if there are errors in it, or if you say like, well, this is a dumb idea and our card doesn't support it, very happy to have that conversation. And then going forward, are there more things that are in scope? So certified devices, as a community, what we're trying to do is improve the tests. That's, I think, the biggest goal. That will make everyone's life easier. We want to help vendors who are interested in certifying devices. You don't have to do this by yourself. Collect these changes for a new version of the spec that, if necessary, if there are shortcomings in the current version, and look at other features in spec. So again, no SRIOV, no SIOV, no ML, at least not for the foreseeable future. But inline crypto is actually the only feature we are currently seriously looking at. To contribute, there are two ways to do this. As a first party, that requires the organization to be an OCP member. We chose OCP as an organization for the spec. So those are the rules. And it requires signing a contributor license agreement, essentially that anything you write in the spec, you don't come back later and say like, hey, we hold a patent on this one. So that's one way. That's how the 4 companies today do it. Or as a third party, anyone can join on the mailing list or our monthly OCP networking call, and essentially first party members can shepherd third party suggestions. All right, with that, the last slide, I was explicitly asked, can you explain a little bit how this standardization process works? So this is our experience, at least at the OCP, which is you find the project, the subsystem within OCP that's of relevance. So for us, that's clearly networking. Go to the networking meeting, talk to the leads, suggest this idea. If they're okay with it in principle, you form a group of people from OCP organizations, a group of contributors. You sign this CLA. There is some legalese involved. And then you develop the draft, and there are two ways to do this. So only the signatories can actually edit the text, but you can do it in the open and get continuous feedback, or you can write a first draft and share that. So that's what we did. We got to some pretty concrete document, and then we shared it with the OCP community for input. We got some really helpful feedback. We iterated on that, went back to the community, etc. Eventually, it was pretty much stabilized. We went back to the project, gave a presentation, got approval that the project was on board with this, and then sort of the end boss is you go to the OCP incubation committee, you give the same presentation, and if they also understand what the value of this project is, then it becomes a spec. And then all the contributors have to sign an updated agreement similar to the CLA that's now called the final spec agreement. So that's where we are today. The V1 spec was finalized in August, and I hope I explained why we did this, what's in it, and if you're interested in any of this, talk to me or join us on the monthly call or on the mailing list, and make this a better spec, and hopefully it's useful to other organizations and people as well. Thank you.
Yeah, I have one comment to the previous slide, if you could just quickly switch.
This one?
Yes. I believe the path is to first present to the OCP project committee and then develop the draft. so that you don't start developing the
Right.
project that committee won't be interested in. And another comment about the whole specification. Is it meant to be kind of a checklist that you publish for your network adapter? Or because I'm afraid that if we start the path that you check all the check marks on the specification and then do the diff as a separate document, this separate document may grow up rapidly as we add more into the base spec. So is it better to make it kind of, to be OCP certified? In this case, you need to give the paper describing the checklist of the features that you support.
So I don't know if I understand the question correctly, but the goal of leaving some wiggle room that for the device is not intended to result in 10,000 pages of things how we differ from the spec, right? So I would expect a device to come with the checklist. Ideally, that's it. And one or two items might be different. Like for instance, if line rate timestamping, if you just don't support that, it's still super valuable to know that everything else is supported and the tests pass.
Yeah, this is exactly like, because in the end, there may be a need for putting a bar of what's OCP certified and what's not. Like,
Yes.
whether you need to be compliant to 70%, 80%, or
Okay.
That's the...
Yeah, that's a fair point. I don't have a good answer. I guess we'll get there when we.
So I wanted to add a comment to that. I think like in the past, WCL has been the standard, right? The Windows Hardware Qualification Library. And I think the point is valid that became the thing. Then you started having WCL certification levels, and was this certified on a given date? And then you ended, because as people add firmware and things change and new features show up, you end up with a diff list that keeps going. So I think one thing that may be worth thinking about is there's a timestamp or a date stamp on when the test suite was run. And if your test suite eventually becomes more firm, right, then you can say it was certified on this day, and then people can go figure out what the hell that means. And typically, and that's what WCL people would do, right? They would basically say, if it wasn't certified this year, don't trust the results.
Got it. That's really good feedback. Thanks.
I'm sorry, is this a pay-to-play thing?
You mean the OCP part?
Yeah, if you're first tier, you got to throw in X, and if you're third tier, you get what? What do you have to do?
I think the first party has to be an OCP member. I don't know the details of what it takes to become an OCP member.
Thanks.
I have a question here.
Yep.
So on my side, I work mostly on embedded projects, and it's on a much lower scale, but it would be very interesting to have the ability to say that, for example, file-side offloading would give you OCP certified behavior on just one part of all of these features. For example, this file, when you add it to your product, it gives you OCP certified timestamping behavior, or MaxSec offloading, or these kind of things. Would it be possible?
Yeah. So can you have a subset? This almost goes, I guess, the opposite of what Srija just said about different Windows levels. But we do have this column required, and we have basically basic, advanced, and optional. And what we had here was we could have an embedded, for instance, level that's even simpler than or fewer requirements than basic. Would that be what you mean, or do you really care about saying like, well, if we're going to implement a particular offload, that is section 5.4 of the OCP spec, that's the way you should implement it. Okay, all right, clear. So actually, one thing I didn't get around to here is the optional sounds a bit weird for a spec, but what we say, there are certain features that many cards implement that we don't really care about. But if you implement them, let's agree that they implement it in one specific way. So that's why we included those as well. Okay.
Yeah, Tom, unless you have a question.
Two questions. One, where are we in that process list that you had? So you had all these steps. Where do you think we are?
At the end for V1.0. So it is a spec.
So it's already been approved?
Yes.
Oh. Second question, for certification, is this free, or do I need to pay for it?
Following the spec, publishing a checklist is free. Getting it on the OCP marketplace is an optional thing, and that is seemingly limited to OCP members.
It's what?
That is limited to OCP members, I understand.
Okay, so the certification itself,
Yeah.
I can't get that unless I'm an OCP member.
No, you can. I mean, there's no it is self-certification is the model here.
Okay, well, I'll be honest. The whole word certification scares me.
Okay.
This is a commercial thing, not a technical thing. And the fact that the spec was approved, how many people have read the spec, by the way?
That's a sizable fraction of the audience.
This is Netdev. This is the primary source of the code.
Which is why I'm here,
It's
right?
a little worried. Yeah, it's why you're here, but I just kind of wish we could have had this discussion before this was approved. That's all I'm saying.
Okay. All right, fair enough. Yeah. I think we tried to summarize, I think what I understand is the view of many in the community already, and we can iterate on this spec if anyone disagrees with what's in there right now.
Well, I think one other point that you said, so regardless of anything, to me, the Linux stack is authoritative. So if we make a change in the stack that now contradicts the spec, it's the spec's problem. And somebody is conforming to the spec but doesn't work with Linux, that seems like that's worse, right? I would rather conform to Linux before the spec. It's just,
Yeah, most of what's in the spec is not something that exists in software and Linux. So RSC and TSO are exceptions in that Linux implements them in software as well as hardware offloads. But for instance, when it comes to checksumming, Linux is actually quite permissive of stuff that we explicitly don't want, right?
So yeah, I haven't seen the updated spec. Also, I'd like to talk offline. I don't quite understand how we can do RSC without being protocol dependent.
You can't. That's actually, even in the spec, we say
you're
protocol
glossing over
independent
that
if you
detail.
can, right? Like in the cases where it's possible, which is most offloads, but it's not this particular.
Okay,
Can
so,
we-
so in that case, is there any part of the spec that says how to do programmable devices? Because that's what you need for RSC,
I think they
right?
said that was out of spec. Anything DPU,
Yeah, no.
etc., is out of spec. Anyway, I'd like to wrap
Okay.
it up.
All right.
We have to be back here by 1:15. I'm sorry for
It's lunch,
the
right?
delays.
Keeping
Yeah,
it-
it's lunchtime.
All right.
Let's give it
Thanks,
up for
everybody.
Willem.